Good day, and welcome to our webcast, Motor Management and Troubleshooting Techniques for AC Induction Motors, brought to you by CFE Media and Technology and sponsored by Lenza, Mitsubishi Electric, and SEW Eurodrive. We're joined today by Michael Lita, Motor Lab Director, and Ronnie Alford, Motor Lab Coordinator, Advanced Energy Corporation. I'm Kevin Parker, an editor with CFE Media. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. Many issues can arise with induction motors, so it's important to learn general troubleshooting techniques. To start, it's vital to understand the operating parameters and forces acting against a motor, to perform tests and make observations based on these parameters, and to remove system components to isolate a problem. Regular measurement procedures, starting with nominal voltage, current, and frequency, can be the starting point for long-running optimal motor and drive operation. This webcast will specify and analyze motor management best practices, along with various troubleshooting techniques to consider, and outline what equipment is needed to identify solutions. Learning objectives for today's session include the following: preview and compare various design topologies and solutions, discuss why certain solutions may be more or less favorable, understand motor management basics, identify the most common issues associated with AC induction motors, review common induction motor maintenance procedures, and finally, learn what it takes to get optimum long-term performance from AC induction motors. This event is a live educational webcast presented on March 10th, 2022. The educational category is Technical, Health, and Safety. Here are some tips to help you get the most from today's webcast. If you experience issues with the slides or audio, refresh your browser or click the Refresh Media button under the presenter's picture. Control the volume of this webcast by adjusting the volume on the computer or on the webcast platform. For technical problems with audio or slides, click on the question mark at the top right-hand corner of the screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask the speakers questions. The live Q&A session will begin after the presentations conclude. Today's webcast is being recorded. You'll receive an email within a week with the link to the on-demand event. To take the Learning Unit exam, use the Learning Unit exam tab option at the top of the screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. We'd now like to share with you some brief videos from today's webcast sponsors, Lenza, Mitsubishi Electric, and SEW Eurodrive.
Getting stressed out by how complex automation can be? Lean on the experts from SEW Eurodrive and check out our MoviKit automation modules. MoviKit is a collection of pre-built software modules for many common motion control applications, ranging from simple drive functions like speed control and positioning, all the way to complex functions like camming and even kinematic robot control. MoviKit makes it easy for engineers of all skill levels to do their own automation. We handle the complex programming part, and you simply enter your parameters and go. Shorten your startup time with configurable automation and motion control functions. No need to waste your valuable time with complex automation programming. Check out MoviKit, the pre-built software modules from SEW Eurodrive.
An enhanced next-generation energy-saving inverter. The Mitsubishi FR F800 series inverter. For fans, pumps, and blowers. Energy-saving operation is achieved by the functions ideal for each application. Our new advanced optimum excitation control improves starting torque and achieves energy saving. With the multi-pump function, a high-level control of water volume is enabled by the PID control operation for up to 4 parallel pumps. With the PID pre-charge function, when water supply to the empty pipe is started, rapid acceleration and deceleration of the pump can be avoided to prevent water hammer action. For any foreign matter clogged in the impeller or fan, the cleaning function is helpful. With the PLC function, the water height and duration can be set. Power consumption can be further reduced. The FR F800 inverter provides a solution for energy saving.
Welcome back. I'd now like to introduce today's speakers. Ronnie Alford joined Advanced Energy in November 2018, having spent the prior 2 decades with the electrical equipment company in various roles in its electrical distribution and motor repair business. Ronnie was involved in field service work, electrical maintenance, and testing, with significant training and professional certifications in these areas. His responsibilities today include conducting motor systems testing, implementing lab improvements, maintaining calibration certifications, and training. Ronnie received his associate degree in HVAC and refrigeration engineering technology from Wake Technical Community College in 2001. Ronnie is also an approved auditor for the EASA accreditation program for third-party quality motor repair. Michael Lita started working for the Advanced Energy Motor Lab in 2010 as a co-op student. After completing an engineering fellowship with Advanced Energy, Michael moved into the Motor Lab coordinator role in 2013. With extensive testing experience in the lab, Michael became laboratory director in 2019. He is involved in motor system testing development, research, and training on a wide range of applications to meet the needs of Advanced Energy's customers. Michael received his bachelor's degree in electrical and computer engineering and minor in mathematics from North Carolina State University. Michael is also a member of the Advanced Energy commercial and industrial team, participating in energy assessments and recommending energy conservation measures at facilities all across the state of North Carolina. Michael, welcome to today's program, and please go ahead.
Thanks, Kevin. Really appreciate it. I'd like to start off by thanking you and Emily and your team at CFE for allowing us the opportunity to come back and present today. Some of the audience may remember we've given a few presentations alongside Kevin in the past, and this presentation is going to piggyback on that. We're going to skip over some of the basics and try to expand the knowledge and the material. So I'd like to start with a brief background and a description of Advanced Energy, and then we'll move on into the slides. So Advanced Energy was founded in 1980 by the North Carolina Utilities Commission to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. We're an independent, nonprofit corporation governed by our board of directors that are appointed by the governor of North Carolina and our member utilities. It was a big year for us back in 2020. We celebrated our 40-year anniversary, and then we continue to work with those member utilities on energy efficiency and conservation projects even to this day. So our current existing member utilities are Duke Energy, Dominion, North Carolina Power, and North Carolina Electric Membership Corporation. In addition to creating means for sustainable energy efficient economic development for the ratepayers in our state of North Carolina, Advanced Energy also operates as a fee-for-service consultant to clients in the U.S. and internationally. We work with other electric utilities, governments, and a wide variety of private organizations in 5 target areas, which include residential, commercial, industrial, solar, motors and drives, where Ronnie and I work, and also electric vehicles. And our customized services include research, testing, training, consulting, and in some cases, program design. So as I mentioned, we're on the Motors and Drives team. Primary responsibilities to Motors and Drives testing and consulting in our lab. Feel free, we have some videos that go into greater detail about our capabilities on our website, www.advancedenergy.org. If you want to learn more about us, learn more about our team and what we do. So at this point, I would like to turn it over to Ronnie, Mr. Ronnie Alford, who will get started with the presentation on troubleshooting techniques for AC induction motors. Take it away, Ronnie.
All right, thanks, Mike, and thank you to everyone for allowing me to present today. During the first segment of the presentation, we'll take a look at some of the forces that act against the motor and problems we may encounter when troubleshooting motors, along with what tools we may use in the process. So first, we'll look at various forces acting against the motor during operation. For a motor to perform within design specifications, running temperature must be kept at or below installation class rating. Applied voltage should be well balanced and as close to nameplate rating as possible, and how mechanical friction within the motor can be overcome during startup. All right. Heat is typically the source of primary damage to motor components. Excessive heat may occur from items such as elevated ambient temperature, unbalanced voltage at the mains, blocked or limited fan cooling, if there is a fan or blower on the motor, motor overload, vibration from shaft misalignment, or even incorrect motor selection for a specific application. All right, so let's dig into the heat. When we talk about heat and motor temperature, you may be wondering what operating temperatures is appropriate for a specific motor. The National Electrical Manufacturers Association, or also known as NEMA, as well as the International Electrotechnical Commission, or IEC, have standardized the operating temperatures. These are defined as installation classes, as you can see here. My motors will be rated within an installation class, which applies to the installation components within the windings inside the motor, but also keep in mind that the bearings and other components will also be rated at temperatures above the class rating. So looking at NEMA rating specifically, you see here the higher the letter, the hotter the motor can get. In other words, Class H installation is rated to run at a higher temperature than a Class F. Always pay attention to motor rated ambient temperatures, as most motors come standard, I would say, to operate in a 40 degrees Celsius ambient. And if that's the case, it should say so on the nameplate. I would also keep in mind that even though you may have a motor with, for instance, a Class F rating, that doesn't mean you'd expect the motor to operate at a temperature of 155 degrees Celsius. Most motors will run much cooler than their class rating. So if you know your application is withstanding ambient temperatures above the 40 degrees C on a regular basis, and the motor runs at a full load most of the time, I would say it's best to order a motor with a Class H insulation. Just knowing that heat is the leading source of motor failures, it is always best to make sure that the proper ventilation and temperature monitoring is always in place as well. All right, so along with temperature, voltage is another force acting on the motor during operation. Now, always verify rated voltage on the motor nameplate. Sometimes you may have multiple voltages on the nameplate, so always double check that the motor was connected for the proper line voltage. And it's always worth noting here that most low voltage motors are typically rated at 460 volt, but grid voltage coming from the utility may be 480 volt. The 460 volt rating there is taking into account a voltage drop in the distribution line coming from the nearest substation or distribution transformer. We have completed testing at our lab here in Raleigh that shows a slight increase in supply voltage above rated voltage will lead to an increased motor efficiency. But at the same time, that testing showed that lower voltages are detrimental to motor efficiency. So according to, Electrical Apparatus Service Association, or ESA Electrical Handbook, if we take a look, a 10% voltage drop causes motor design torque will be reduced by approximately 20%. In general, if lower voltage is supplied to the motor would need to draw more current to the output to provide the necessary torque and speed for the application, and therefore, higher current draws will lead to, overheating and motor failure. All right, continuing to look at voltage. Voltage unbalance is another major problem. We've had quite a few metering and verification projects where we saw large amounts of voltage unbalance. We work with utilities, as Mike stated, very often, and the utility will typically have a power purchase agreement in place with your facility, that sets limits on the amount of voltage unbalance that they can provide. Typically 2 to 3%. That doesn't seem like much, but even 2 to 3%, as you see here, can be detrimental to your motor population over time. The point to be made here is that even minor voltage unbalance can lead to horsepower derating for your motor. And you'll see here in the chart shown from NEMA MG1, which I like to call our motor Bible, shows that voltage unbalance exceeding 1% can lead to derating and excess heat. So always keep in mind that voltage unbalance directly leads to current unbalance. Industry rule of thumb is that for every 1% voltage unbalance, a motor can see 7 to 8% of current unbalance. So a high current unbalance is detrimental to the motor operating conditions. Again, higher currents on individual phase can lead to hot spots in the motor, windings, and thus early failure. So of course, the voltage unbalance isn't the only cause of current unbalance. Unbalanced winding resistance can also lead to current unbalance. If you're measuring a current unbalance in the field with an amp meter, with your motor loaded or unloaded, then it's always a good idea to de-energize the motor and measure each phase, or measure each phase-to-phase winding resistance to verify the baseline unbalance. All right, so we'll get into the third and final force acting against the motor that we'll cover today is mechanical friction. Mechanical friction is directly dependent on the motor bearings. A good place to start is within the motor alignment to the load. Parallel or angular misalignment can lead to many problems over time, but is especially critical to controlling vibration and mechanical wear on the motor. And keep in mind that all motors must meet manufacturing tolerances. This is the case if the motor is new or just been repaired. Some of these key tolerances include rotor balancing, shaft runout, bearing housing, bearing journal fits, shaft passages. So, a key factor is that the correct bearings are being used for the application. For instance, standard ball bearings would be used for direct coupled loads or lower torque belted loads. Roller bearings would be used for, belted applications with the higher radial loads. If you're thinking about vertical motors, in your facility, consider whether you have an axial force that may be upward or downward or balanced to determine if you need a thrust bearing on one end of the motor. And if that's the case, most commonly matched with a guide bearing on the other end. But just to reiterate, bearings are the number one cause of motor failure. So it is very important to follow preventive maintenance routines with your bearings, such as periodic lubrication, vibration analysis. Even when greasing the bearings, verify the proper lubricant is being used and the proper amount of lubricant is being added. The most recommended grease type that we see these days in the field is Polyrex EM. And remember that bearings should be maintained based on run hours. So there's product literature out there from the bearing manufacturers that can give you specifics, details on lubrication types, intervals, the amount of grease to add. So a quick review. We now understand key forces that act against the motor during operation. So let's move on to what are some of the problems to look for when troubleshooting motors and what tools we may use. One key factor that plays a part in troubleshooting motors is knowing the motor data and the motor's history. So when talking about motor data, we want to confirm that the motor in service is appropriate for the application by verifying its mechanical and electrical characteristics are correct. We can accomplish this by first collecting data from the motor's nameplate. Secondly, when we talk about motor history, we're talking about how long the motor has been in service and how much runtime the motor has encountered. When troubleshooting motors, if you think the motor failed prematurely, then not only do we need to look at the in-service time, but it's also a good idea to know how long the motor was out of service before running. This meaning, was the motor a spare that had been sitting on a shelf for a period of time before it was installed? Or does the system have multiple motors that are used for the same process? There are many cases where motors will sit for months on end, where there is no controlled environment, and the motor shaft is never rotated. So this can lead to many premature failures, such as flat spots on the bearings or moisture buildup on the linings of the motor. Therefore, it makes it important part of the troubleshooting process. All right. So this may be a little small here, but let's look at a few steps to take when moving forward with eliminating problems that may be encountered with our motor during the storage process. So I think this is one that gets overlooked sometimes. Here you will see a motor storage tag, courtesy of ESA, to give us a great guideline on the data that we should be taking monthly on our stored motors. And first you'll see that we're documenting when the motor was put into storage, when we will lead into documenting monthly what our IR or insulation resistance value is monthly. This can easily be captured with a handheld megometer at the motor leads. This will help us trend if there is any type of insulation breakdown being created from moisture or contamination. Last, you will see that we're documenting that the shaft has been rotated monthly. When following through with this process, you're making sure to rotate the shaft completely 1 or 2 times and then line the keyway up with the design position. This allows for the balls or rollers in the bearing race to move and for the grease to be able to rotate completely around the surface. Not only are you looking to prevent premature bearing failure with this task, but also any shaft sagging and larger motors that may occur. And I'll also note here that this is a service that most of your motor repair facilities offer, as well nowadays, including off-site storage. That may be the best option if you cannot provide a clean or climate-controlled environment. All right, now that the first key step has taken place and all the proper procedures have been followed, we can move into looking at a few of the basic mechanical inspections. Here, when performing any kind of troubleshooting, do not get ahead of yourself in the thinking process. I always say, look for the obvious signs first. Some simple but important things to look for when performing a mechanical inspection would be, look for hot spots on the motor frame, such as discoloration of the paint. If the motor has withstood enough heat to show signs of external hot spots, then we know it's a good sign. It gives us an idea of the degradation the components inside the motor have seen. So, we would look for leaking lubricants, under and around the motor. Leaking lubricants can play a big role in understanding if the motor bearing grease is getting too hot, or if the motor bearings are not getting enough lubricant. So broken or missing parts is always an easy but effective inspection. Broken or missing external fan blades can play a vital part of troubleshooting, as a motor with accelerated temperature or even high vibration due to an unbalanced fan factor. We can look inside the motor J box or terminal box for any signs of arcing, loose connections, or even water damage. As we touched on earlier about motor enclosures, it's always a good practice to look for blocked airway paths. For example, TEFC motor. There are a lot of applications that can cause the fan cover vents to get blocked from materials in the environment. So for example, damp paper or sawdust particles, rock dust. There are so many different contaminants that can produce cooling problems. But sometimes it's just basic human error of leaving a box too close to the motor, or adding components sometimes to a motor to what we think will help with the contamination buildup, but not allowing enough room for air to flow properly past that component. So once the basic visual inspection has been performed, move on to check for rotation of the shaft by hand. Is the machine free to rotate? If you cannot rotate the motor shaft when coupled to your driven machine, then uncouple the motor and check for free rotation of the motor shaft, and listen for any noise coming from the rotating parts. A lot of times it's easy to hear or even feel a bad bearing or rotor dragging, inside the stator. So in some cases, you're suspecting a mechanical issue before it becomes a failure. You notice high vibration coming from the motor, but not very clear on where the source is coming from. In this case, that's when you can perform, vibration analysis. So vibration analysis, is one of the most common mechanical tests for preventive or predictive maintenance. This test is performed by using a FFT spectrum analyzer and using an accelerometer that's usually placed, in the horizontal vertical planes of both bearings, and actually on at least one of the housings. There are standards that apply to acceptable limits of vibration, but make note that the standards such as NEMA state that acceptable limits apply only to uncoupled motors, so you want to disconnect it. So NEMA acceptable limit is 0.15 inch per second peak for resilient mount motors and 0.12 inches per second peak for rigid mount motors. So to help clarify, the limit is higher for a resilient mount motor due to the movement that is allowed, by the rubber or the type of isolators used during mounting. So this is normally seen in smaller motors, such as on a fan or blower application. So I recommend always taking vibration readings of the motor coupled to the driven equipment first, as this can also pick up any signs of misalignment, coupling wear, or even unbalance of driven equipment. All right, so now we've looked at a few of the different types of mechanical test methods. Let's take a look at a few of things to focus on during the electrical inspection portion of troubleshooting. Just that as any portion of the troubleshooting process, start with the basic tasks again, work your way to the more in-depth testing processes. First, we should know that it's best for these tests to be performed by someone who has been trained, in the electrical testing for safety purposes. By using a voltmeter, we could first check for applied line voltage at the power supply of the motor at each line to ground to eliminate any potential, blown fuses. And then we could proceed to test each phase, line to line. The applied voltage could be direct wired from a simple on-off switch, or it could be coming from somewhere a little more complex, say such as a VFD or soft starter. So when performing these tests from a control circuit such as a VFD, we will want to ensure that the proper power is available at the incoming and outgoing side of the unit when in run mode. So, another useful test to perform when troubleshooting the motor with an electrical fault is the ground wall and continuity test. So, but just make sure, if your motor is powered by a VFD or a soft starter, that you disconnect the motor leads from that device, before beginning these tests. So, the continuity test can be performed with an ohm meter. It should be tested from the leads coming directly from the start switch or VFD. By doing this, can eliminate any possible broken power cables that may be running in conduit or underground. If the continuity test fails, disconnect the power cable at the motor and perform the test again between each phase of the motor to pinpoint if the failure is in the motor, or in the power cables. If no cause of failure has been determined at this time, then you could move on to performing an insulation resistance test that checks for any ground faults in the ground wall insulation of the power cables or motor leads. As we spoke about earlier in the motor storage section, this test can be performed by using a mega ohm meter, and you will see in the upcoming exercise on the next slide how this test can be beneficial. So here we're looking at an example of a 460 volt AC induction motor that will not start. Once we go through the preliminary tests that we covered earlier on testing for supplied voltage at all three phases and eliminating any blown fuses, we move to the next system component. The control circuit is tested to make sure proper supply voltage is coming out of the unit. If a fault is coming from the VFD or soft starter, use the code given to help troubleshoot that problem. If a grounded motor is suspect, this can be tested by performing the insulation resistance test, or also known as the hour test. With this test, the mega ohm meter applies 500 volts DC to the motor and measures the resistance of the insulation to ground. The applied DC voltage is why it's important to remove the motor leads from any control circuit, to prevent any damage. The recommended minimum insulation resistance value at 40 degrees C for most motors with random wound stator coils with DC voltage applied for 1 minute is 5 megohms. So low readings may indicate reduced insulation conditions that could be caused by contamination or deterioration from excessive heat. If the motor tests at 0 megohms, then we know that the motor winding circuit is grounded and the motor will need to be repaired or replaced. But just keep in mind, note that a mega ohm meter cannot determine, if a complete motor winding circuit is good, as well as determine, turn-to-turn or phase-to-phase faults. These tests will be performed by, more advanced motor circuit testers. So we have learned from all the considerations that we have looked at today to perform tests and make observations. We understand the operating parameters and remove system components until you isolate the problem. You'll see here that I listed a few of the standards, that we've ran through today, along with a few additional, that we use every day in testing and also in the motor repair field. Good ones are the IEEE 112 standard for test procedures of polyphase induction motors and generators. Again, the NEMA MG1 standard for motors and generators, and also the ESA AR100 standard for recommended practice for the repair of rotating electrical apparatus. They're all great references to use when troubleshooting AC induction motors and are looking for specific guidelines in troubleshooting or motor testing techniques. All right, with all that said, that covers some of the key forces that act against the motor and a few troubleshooting techniques to consider. And I'll now turn the presentation over to Mr. Michael Lyda, who will walk us through motor management processes. Take it away, Mike.
I appreciate it, Ronnie. Great stuff. Ronnie's very active on the ESA Technical Electrical Apparatus Service Association Technical Committee. So, Ronnie, you could call up if you're an ESA member, or, even if you're an end user, you can call up and get some of Ronnie's consulting services there through ESA or through Advanced Energy. We always love to see, when there are issues. It's always great to see the stories because, some things seem unbelievable until you see the evidence. So definitely the troubleshooting, that's where a lot of the fun stuff is. So I'll be covering the last topic of our material, motor management. By the end of this part of the presentation, I'm hoping you'll have a good idea. If you don't have a motor management system in place, hoping you'll have a good idea of where to start and a couple of things that you can get started on, tomorrow, next week, next month, whatever. Or if you do already have a system in place, maybe you can learn a few things today that can help you improve that existing program. Good motor management system really should, make your life easier, your plant's life easier. It's going to reduce costs, reduce inventory, and then also should reduce energy usage. So I'd like to start with a few numbers to kind of get you in the mindset of motor management and why it's important. The average motor consumes at least 50 times its purchase price in electricity usage over its lifetime. That's a huge amount. Motor purchase price only accounts for about 2 to 3% of the motor's lifetime cost. And then a small percentage of that lifetime cost is for maintenance and upkeep. But the overwhelming majority of that lifetime cost of an electric motor is in its electricity usage. So that's kind of an eye-opening thing for me. And then the last bullet there, we're estimating less than a third of end users may be considering energy costs when looking at purchasing new motors, or if you're making the decision of repairing or replacing a failed motor. So hopefully, by the end of the presentation, we've got about 20 or so minutes left. Plus we got some time for questions at the end. So maybe about 15 minutes worth of material. Hopefully by the end of the presentation, you'll be considering energy costs in your purchase decisions, not just that sticker price when you go to your distributor and say, hey, I need a new motor. So for those reasons and many others, all the facilities using electric motors should really have a set of guidelines for managing the motor population. And that's kind of what we group into this topic of motor management. So what are the components of the motor management system? So we list three. We call it a policy. So purchasing, then operations and maintenance, which a lot of what Ronnie just went over, and then the third component, making that decision, when to repair, when to replace. So what are the benefits of a good motor management system? Energy savings, cost savings, increased production, shorter downtimes. Put all that stuff together. Those are all keywords. What does all that mean? It means happier management, right? Happier managers, lower stress work environment, and that's what we all are striving for. We want to come in, do our jobs, get the jobs done efficiently. Motor management is going to help you do your job better, right? And if you are the manager, it's going to help your plant work better. So I would like to start, here with just an example. I was in a plant not too long ago, so I'm going to use them. won't mention any names, of course, but I'm going to use them just as an example. So say you're the maintenance guy, maintenance personnel, maintenance supervisor, textile plant. They make the input. They have cotton on the input, and they have yarn on the output. So the plant must be kept at a certain temperature and humidity to keep the yarn moving on those spinning machines. You got to keep the product moving. If the humidity gets out of control, then the yarn bunches up, comes off the spinning machines. You have to spend labor hours aligning the yarn back onto the spinners. So one way that you can help control that temperature and humidity, a very common way in the textile industry, is with air washers. So what if, one of your critical air washers stops working? All right. Worst case scenario for the plant. You shut down the process. Humidity is changing. Humidity is going up in your plant. Temperature is going up. Figure out air washers down. You follow some of the methods Ronnie mentioned earlier. Verify motor, and then once you've done that, you verify if the motor winding resistance isn't showing up right with your multimeter. Then you do bring your megger out, do an insulation resistance test. The motor's failed for whatever reason. So if you had a motor management system, you refer back to your program documentation, and then without having to think about it, that you have a backup for that motor, and where it's at, and it's labeled. So you disconnect the failed motor, you go pull the spare motor from the inventory, you wire it up, you align it. Within a few hours max, your air washer is back up and running. Then the plant comes, you bring the plant back online. Plant process continues. Within a few hours, you minimize the downtime, and even through like a full plant shutdown. Now, what if you didn't have the motor management program? And then let's assume, this is maybe something very common for the last few years, assume you were out sick that day. So if the air washer motor fails, what's the plan for replacement? Are you the only person in the plant who knows what to do if that motor fails? Wouldn't it be valuable to have a documentation that your colleagues or someone else could refer to, that in the event of a motor failure, especially for critical motors, this is a motor that the whole plant depends on. So working motor management system and documentation really changes and helps you keep up with your maintenance across the whole motor population. And that can easily be passed to other trained personnel in the plant. It helps save labor hours when there's staff turnover. That very important today with labor shortage and, folks definitely moving around jobs a lot more often than they did 20 or 30 years ago. So we're going to talk about now kind of some of the aspects of the motor management program, and hopefully you can take that example and, you may not work in a textile plant, but I'm sure it will apply to some motor similar to the air washer motor at your plant, those critical motors. So you're ready to create a motor management system. How hard is it? It's not that hard. The first step, you're going to want to come up with guidelines for your three main components. So we'll start with purchasing. So very straightforward. You need to develop a purchase specification. What goes into that purchase specification? You're going to normalize the brands that you use. Maybe you got a certain motor that you like, a certain manufacturer or a couple manufacturers. Specify model numbers. Consider life cycle cost in purchasing instead of looking at just initial cost. For your critical machines and your critical applications, you're definitely going to want to purchase backups. When you purchase the backups, it builds up your spares inventory. If you use similar motors across many different applications, you may be able to limit the amount of spares you have to keep on site. Maybe storage is an issue. That's a good start for purchasing. All right, operations and maintenance. Ronnie covered a lot of that stuff earlier. Routine maintenance on the motors. Focus more time on critical motors. Motors with high usage rates. Motors that are over 4,000 to 5,000 run hours per year. And then the last component, motor repair. So with the back to the repair shops. So definitely recommend using the certified repair shops for your motor repairs, and even ones. So when I say certified, that's repair shops with third-party quality repair accreditations. We'll go deeper into what third-party quality repair accreditation means in a few minutes. And then just like for purchasing, develop your motor repair specifications as well. So if you're using a certified shop, they can help you create a repair specification. And if they don't, then that's surprising. You may want to consider a different shop or something like that. Some areas you may not have options. You may be limited to the shops, but in most areas you should have at least a couple of vendors that you can compare their services. Next, here we're going to look at an example. So life cycle costs, initial costs versus operating costs for a motor and a car. So I mentioned earlier that only 2 to 3% of an electric motor's life cycle costs is in its initial purchase price. And the remaining 98% is electricity cost. So this example here compares the life cycle cost of that 75 horsepower motor and then a standard medium sedan. So medium sedan, think Honda Accord, Toyota Camry, Chevy Malibu, Nissan Altima. Those are some of the more popular cars on the road, kind of high volume cars. So notice that purchase price and look at the annual usage, the efficiency on the motor side, 95%, car 30 miles per gallon, fuel costs, and then lifespan. We'll then take all of those variables to calculate the life cycle costs for each product. It's kind of a hot button topic right now, so not surprisingly, the average price I've listed for the regular gas has increased quite a bit since I made this slide deck just last week. But even with the higher fuel costs, the concept doesn't change. So here's the kicker. You see in orange at the bottom of the screen when we look at life cycle cost and then operating cost as a percentage of the life cycle cost. So the initial cost of the car is 7 to 8 times that of the electric motor, but the life cycle cost for the motor is about 4 times that of the car. So why is that? All the electricity in the electricity bills, that's where all the money comes from for running the motor. So some of you may be involved in the billing or energy stuff at your facility, so it may not be news to you, but for others, and when I first saw this, it's very eye-opening. So next, we're going to go into a few slides into a little bit deeper into each of those 3 motor management components. So first, the motor purchasing policy. That's step 1. So standardize your purchasing. It's going to make it easier to order the products you need, get them into your plant faster, and it's going to save you labor hours. So your purchasing staff, and some of you on the phone may be purchasing staff, need to have proper training so that initial cost isn't the only factor in the equation when you're making purchases. So as we just saw from the example, the initial cost actually has very little impact on life cycle cost. You may want to pre-qualify your vendors. In some cases, you may want to perform testing. Our lab in Raleigh specializes in this. We have plenty of examples where we've done testing for original equipment manufacturers. Not going to go into any here, but testing, third-party validation, not always necessary, and maybe could be a little expensive in some cases. So very valuable if you're making a huge decision on which vendors to use for your specific plant and your specific applications. Next, here we'll just spend a few minutes on motor repair. We're coming up on the end of the presentation. So motor repair, third and final component of the management system. Step 1 with your motor repairs is ensure your vendor is providing quality repairs. So similar to developing a purchase specification, you should build or develop a motor repair specification. So you see many items listed here in the slides: repair breakpoint and specifications for motor repair that can be added to your repair specs. Repair breakpoint, that's going to be different for every facility. So just as an example, a common specification may be that you repair all motors over 75 horsepower, but replace anything below. Just an example. Another example specification could be to replace any motor that costs over 50% of the replacement cost to repair. The general, straight line specifications like this may not necessarily work for your facility if you have motors that are really old, predating any kind of efficiency regulation. So really old, maybe inefficiently designed. So that's where a horsepower breakpoint study can really help you. And that would be tailored specifically to your facility, not just a general example, kind of like what I just mentioned. So the breakpoint study will take into account not just repair versus replacement costs, but also the energy savings you'll earn with an energy efficient upgrade. And then, as I said earlier, you definitely want to use the accredited repair shops. So a few of the third-party quality repair programs available in this industry include the ESA, Electrical Apparatus Service Association accreditation, SKF certified. The Bearing Company offers some accreditation for repair shops, the Green Motors Initiative, and even Advanced Energy. We have our own program called Proven Efficiency Verification, or AE certified. Each of those programs listed really has its own distinctions and on, the good and the bad there's a good and the bad of each program. The main goal of any of the accredited repair programs is ensuring that the motors are being repaired to the highest quality and the process is being used, standardized, followed, time in, time out, every single motor. Speaking of high quality motor repairs, we have an example here that we like to show. This is what can happen when quality control procedures aren't followed. So you see two performance curves. This is the same motor, 10 horsepower, 1800 RPM, 4-pole motor. Nameplate, full load efficiency at 100%. Load is 91%. So the orange line here, the top line, shows the efficiency when the motor was repaired, including a full bearing replacement, top of the line motor bearings, proper greasing. Then the bluish green line below shows the efficiency results from testing when the motor was repaired with low quality bearings and under greased. So you see a large gap between the efficiency performance of that same motor. So it's vital to make sure the repair vendor isn't making mistakes like this or using low quality components or something like that, trying to save money, cut costs, or else you'll then be losing money and electricity when you put this repaired motor, a poorly repaired motor, back in service. One last point I wanted to make on the repair and the repair vendors. So they're happy to have your business. They want to help you. They'll be happy to keep records for motors they've repaired for you or recondition. So they can be very helpful in your management system tracking. You don't necessarily have to take all of that information in-house. Just keep an open line of communication with those repair shops and your distributor and utilize them as much as you can. So last material here, just creating your motor management policy. Once you have the system in place, keep track of the motor failures, track your energy costs versus production. Use those numbers to update and improve your policy as you see fit. And this, keep in mind, this isn't a one-time exercise that you just sit down and you build a spreadsheet. This is something you do. You keep your personnel trained. You stay trained. And you want to constantly be improving your motor management. And that's how you're going to really maximize the reliability of the motors in your facility and maximize your savings. So in summary, when you're purchasing motors, use those life cycle costs instead of the initial costs. Think of that table that we presented. Develop and use the purchase specifications and repair specifications so you get the best motors for your specific applications and also the highest quality repairs. And then finally, utilize the strategic preventative maintenance techniques to upkeep your motor population and extend your useful life. So at this point, I would like to turn it back over to Kevin, and that'll conclude my portion of the presentation. Kevin, take it away.
Well, thanks, Michael. We've got a lot of questions and only a little bit of time, but our audience, bear in mind that we're going to post the answers to the unanswered questions with the webcast archive version. And we also very often include these webcasts in the magazine and online as well. So getting right to it, Ronnie, you were talking about how dangerous high temperatures can be for motors. But are there some conditions that require heaters in motors?
Yes, thank you, Kevin. Hopefully you guys can hear me clear. That's a great question. So, heaters are always recommended, I would say, in motors that are in an area where they can reach a temperature, below dew point. Of course, there's varies largely with pressure and humidity, of your location, but this can often happen when, motors are sitting in storage or in an application where the motor is not always running. So, if it's outside, you have dramatic temperature changes. Here in North Carolina, we see a lot of humidity. So that motor is not running, then you're going to want to have some type of heaters in that motor.
Good. A question for you, Mike, and I'm afraid this is going to have to be our final question of the day. How does incoming supply voltage unbalance lead to motor failure?
Yeah, that's a great question. I know Ronnie touched on this a little bit earlier, but it's a very important question, and this is something to definitely keep an eye on the facility. So, you have the unbalanced supply voltage, which leads to unbalanced line current, and like we said, for every 1% voltage imbalance, expect about a 7% current unbalance. So current unbalance means you have, at least one of your phases is going to be running if the motor's at rated load. At least one of those phases is going to be above the rated current of the motor. So you have the one phase, some of the windings are heating up, outside of what would be expected under normal operating conditions. You develop hot spots in the motor, and then hot spots over time lead to, electrical failure, definitely decrease performance. But then, if you leave it that way for a long time, decrease reliability, and then potentially electrical failure, maybe a line-to-line short or line-to-ground short or something like that. So very important for the voltage imbalance is very important, something to keep an eye on. There was another question in the Q&A about, how what to check voltage imbalance with. Simple multimeter is good if you have access to the motor terminals and do it safely. If you have some, more higher tech equipment, that's also good, but a simple multimeter, you can check the three phases or each phase to ground, and you'll be able to tell right away kind of if the numbers are the same or if they're quite a bit different.
Great. Thanks so much, Michael and Ronnie. That really concludes the time that we have. Be sure and check within the next week for the answers to your questions, which, as I say, will be posted online. I'd like to extend special thanks to our sponsors, Lenza, Mitsubishi Electric, and SEW Eurodrive, for sponsoring today's event. And now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcast. Finally, on behalf of CFE Media and Technology, I'd like to thank you all for attending. That includes our webcast. Thanks, and we'll see you next time.